Hello everyone. So in this video we are going to solve some of the gate questions which is related to the topic which we have already covered, that is linear time invariant system and basic signal properties. So this will help you to gain some knowledge about the competitive level questions. So to start with, we will start with the question which came in GATE 2017. The question says that the input xt and the output yt of a continuous time system are related as this expression. The system is, so we have to check about the linearity and time invariance property. So all options are the jumbled version of these two properties. So we have to focus on these two properties. So let's solve this problem. So we have our relationship as yt is equals to t minus capital T to t xu du. So as we all know that integration is itself a linear operation, though you can prove it, but as a universal rule you can take it as that the integral operation, so integral operation is linear because it follows both the property, that is additive property and homogeneity. So that's why the integral is linear operation, and here you can see that we are integrating the input and getting the output, so it's a linear operation. So the system is linear. Now to check the time invariant property, what we will do, we will shift the signal by some definite amount and see that the same shifting is done at the output or not. If it is happening, then we can say that the system is time invariant, otherwise it's a time variant signal. So let's solve the second part. So second part says that suppose we will take output relationship as y1t, which is equals to integration t minus capital T to t x u minus tau d. What we have done, we have shifted the, so shifting by constant tau. So now in the next step what we will do, we will replace this u minus tau as lambda. That implies that our du will be d lambda, and again if our limit for u is changing from t minus t to capital small t, then the limit for our lambda will vary from t minus capital T minus tau to t minus tau. So you can get this range from this expression. So let's write the expression for y1t, which is equals to t minus capital T minus tau x of lambda d lambda. And from our original expression, what we can write, y of t minus tau as t minus tau minus capital T minus tau xu du. So to write this expression, we have just replaced t as t minus tau in this expression. So we got this. And when we compare these two, so you can see that y1t is equal to y of t minus tau. So if we are shifting the output by an amount t minus tau, that is replicating to the output as well. So what it says that our system is time invariant. So we have to take the option linear and time invariant. So the option B is correct. Let's move on to our next question. So next question says that, and that question came in GATE 2015 exam. So it's an 1 mark question. The question says that the result of the convolution x of minus t convolved with delta t minus t naught is. So here we have to see the property of delta, that is impulse function. So here what is written, del of minus t naught. So we can take the minus common, so we can write it as t plus t naught, and as we know that del of minus t is equals to del of t, you can also check this property. That's a very easy way to check this property, and that will be equivalent to del of t plus t naught. Now what we will do, we have to convolve it with the x of minus t. So now x of minus t is convolved with del of t plus t naught. So what will happen, the output will get sampled at this time instance. So what will be the output? Output will be x of, just replace the variable t as t plus t naught. So I will write it in a proper manner, t plus t naught, and what it will give? It will give x of minus t minus t naught. So as you can see that the option 4, so D option is correct. So this is the output. This question is related to the basic property of impulse signal, that convolving it with any signal will give the output of that signal at the time instance at which the impulse is given. So here t minus t naught is the time instance, so we have to replace the t with t plus t naught. Now moving to the next question. So the next question says that the impulse response of a continuous time system is given by ht is equals to del t minus 1 plus del t minus 3. The value of step response at t is equals to 0 is. So this question came in GATE 2013 exam. So here the point is that we don't need the impulse response, we need the step response. So first we have to know the relationship between impulse response and step response. So the step response is equals to minus infinity to t h of tau d tau. As we all know, this is analogous to our unit impulse signal and unit step function. So the relationship between unit step function and unit impulse signal is equivalent to what we are writing here as impulse response and step response. So st will be, that is st is here is the step response and ht is your impulse response. So integrating your impulse response will give you the step response. That is the basic idea. So we have this impulse response equation given by this, so we have to just replace it here. So the st will be equal to minus infinity to t del of tau minus 1 plus del of tau minus 3, and that will be integrated to d tau. And we all know that integrating an impulse signal will give you the unit step function. So u of t minus 1 will be the output plus u of t minus 3. So integration of u tau minus 1 will be this, and u of t del of t minus 3 will be u of t minus 3. So now we can plot this signal to get the output. What is the output? So just to plot, so first we will plot the function u of t minus 1. So as we know that it is a shifted version of unit step function by a unit 1 to the right. So the system, this function starts at a value of 1, and the value greater than 1 it will take a value of 1, and for all values which is less than 1 it will take a value of 0. So here what we have u of t minus 1. Similarly, u of t minus 3, you can directly write that it is a shifted version by 3 units. So this is your 1, this is your 2, this is your 3. So the output will be this one. So any value greater than 3 it will take a value of 1, and any value which is less than 3 it will take a value of, so this is your time axis t, and this function is u of, so I will write with a different color, u of t minus 3. Now we want the summation of these two, so we have to just add. So as we can see, for the range of 1 to 3 both signal has different values. So the first signal has a value of 1 and the second signal has a value of 0. So when we will add, we will get 1. So from 1 to 3 the value is 1, and from 3 onwards both the signal, so this is also 1 and this is also 1, so this will add up to 2. So from here onwards we will get a value of 2. So this is 2, and this is your time axis at 1, 2 and 3 and so on, so 4, 5 maybe. So the question says that we need a value at t is equals to 2. So we have to just mark what is t is equals to 2 and we'll get a value of 1 here. So what will be y of 2? That is equals to 1. So the output value will be 1. So we have to just mark the option B, which is correct. Now, from GATE 2012 exam, this is a 2-mark question. The input xt and output yt of a system are related as yt is equals to minus infinity to t x tau cos of 3 tau d tau. And we again have to check the system property of time invariance and stability. So we have two different properties, that is one related to time invariance and other related to stability. So we'll check these step by step. So let's solve this question. So what question says, suppose we have an input of xt, we'll get an output of yt, and that yt is related to this input as t is equals to minus infinity to tau. So this is tau to t x of tau cos of 3 tau d tau. Now to check the time invariance, what we have to do, we will shift the input by an amount. So suppose we have taken x of t minus t naught. So the output, suppose we have some y dash t, then it will be equal to tau from minus infinity to small t x of tau minus t naught cos of 3 tau d tau. Okay, and now we'll replace tau minus t naught as some tau 1. So by replacing, what we'll get y dash t, we'll get y dash t as tau 1 from minus infinity to t minus t naught x of tau 1 cos of 3 t naught plus 3 tau 1 d tau 1. And from the expression, original expression of yt, we can write, suppose y t minus t naught as, so this will be equal to tau from minus infinity to t minus t naught x of tau cos of 3 tau d tau. And when we compare equation number 1 and equation number 2, we can say that y dash t is not equal to y t minus t naught. So y dash t is obtained by shifting the signal with an amount x of t minus t naught, and y t minus t naught is shifting the output, and these two are not same. So that signifies that our system is time varying. So the system is time varying. Now we have to check for the stability. So we have to check for any bounded input. If the output is bounded, then we can say the system is stable, otherwise it's an unstable system. So next we have to check the property of stability. So we have to take a bounded input and we have to check that the output is bounded or not. So we have taken a bounded input xt as cos of 3t ut. So this is a bounded input. Now yt will be 0 to t cos square 3 tau d tau. This is from direct replacing it in the equation. So when we integrate it, what we'll get? We'll get 0 to t 1 by 2 d tau plus 0 to t 1 by 2 cos of 6 tau d tau. So this is basically using the property of cos 2 theta. So you can directly write it as like 1 by 2 1 plus cos of 6 tau is equals to cos square 3 tau. So this is the property from the property. You can directly write it. And as you can see that if you add, suppose t will tend to infinity. So if t tends to infinity, both of the integrals. So we'll say that the first integral is represented by a value of I1. So this is I1 and this integral is represented by I2. So when we put t tending to infinity, so if it is 0 to infinity 1 by 2 d tau, that will lead to a value of infinite. So the integral I1 and I2, here I1 will tend to some value of infinite when t tends to infinite. So I1 will also tend to infinite if t tends to infinite. So the system is not stable. So you have to mark the right answer as. So first we have seen that this is time varying also and it's not stable. So this is time. So first it's not stable and it's not time invariant. So not time invariant signifies that it's time vary. So the option 4 will be correct. So now we'll solve the next question, that is a system with input xn and output yn is given as yn is equals to sine 5 by 6 pi n multiplied with your xn, and the system is linear, stable and invertible. So we have to check three properties: linearity, stability and invertibility, and we'll then mark the correct option. So for linearity, it is very evident that yn is dependent directly on xn. So we can say the system is linear. So you can directly say that yn is proportional to xn. So that's why the system is linear. So linearity is very simple to check. Also the stability is also very simple to check, because if we choose any xn, that is any xn which is bounded, the value of sine 5 by 6 pi n will lie between some -1 to 1. So the output will not be bounded, unbounded. So that's why yn will always be less than or equal to xn. So it will be equal to xn when sine 5 by 6 pi n will take a value of 1, and otherwise it will be less than that value. So if xn is bounded, then yn should also be bounded. So what it signifies that the system is stable. So we have checked linearity and stability. Now we have to check the invertibility. For invertibility, we have to check that it's one-on-one mapping, that one input will give only one definite output. So suppose we have taken some input as k delta n. So where k is any integer. So any input k delta n will give the output as 0. So it is not one-on-one mapping. So that's why the system is not invertible. So what it says, that suppose we have this function and any value of xn, suppose we have taken 2 delta n or some 5 delta n. So for all these values the output is 0 and so on. So k delta n, the output will be 0. So all these values are giving the same output. So it is not one-on-one mapping. So an invertible system cannot be made. So that's why the system is non-invertible. So what will be the correct output? We have linear, stable and non-invertible. So option C is correct. So we have linear, stable and non-invertible system. So finally we have another question from GATE 2014, and it says that consider a discrete time signal xn which varies from 0 to n when, so it takes a value of n for n varying from 0 to 10 and it will take a 0 value otherwise. So if yn is the convolution of xn with itself, the value of y4 is. So here it is saying that we are convolving the, so the output basically is x of n convolve with x of n. So this is your convolution, and we want the value of y of 4. So suppose how we can write it as like summation x of k x of n minus k from the definition of, so k will vary from minus infinity to infinity. So from the definition of convolution we can write this expression as this. Now so we want the value of y of 4, then it will be equal to summation x of k, just for brevity I am not writing the limit again and again, x of 4 minus k. So we have x of k and x of 4 minus k. So let's plot these two equations. So we have first xk, and xk we know that it will take a value of n for 0 to 10. So it will take a value of 0 for n equal to 0, it will take a value of 1 for n equal to 1, and so on. So let's plot this function. So this is for x of k. So x of k is taking 0 at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So it will take a value of 1, then 2, then 3, then 4, then 5, 6, 7, 8, 9 and some 10 value. And similarly x of 4 minus k can be represented as x of minus k plus 4. So it is basically the operation in which what we have to do, we have to first advance our signal. So it will be advancing our signal by 4 units and then inverting it. So it contains two operations. So how the plot of x of 4 minus k will look like. So as it is taking negative value, we will draw the axis in the middle. So the value will be it will be 0, this will be 1, this will be 2, this will be 3, this will be the 4 value, 5. So 1, 2, 3 and this value is 0, but the axis is 4. So here this is 4, this is your minus 1, minus 2, minus 3 till it will go to minus 6, and the value will increase. So this value is 0, 1, 2, 3, 4, 5. So I am not drawing all this. So this minus 6 value will take the value of 10. So these are the two plots. Now what we have to do, we have to multiply each one of them. So suppose we have taken x of 0. So x of 0 will be multiplied to x of 4, and then we have to add so on. So for all the values of k we have to add. So how it is done? So summation k is equals to 0 to 4, x of k, x of 4 minus k will be equal to, so the value of this will be 0, then 4 plus 3 plus 4 plus 3 plus 0, and the value will be equal to 10. So this is the output. You can just have to so I have made a mistake. So here we cannot say it is a infinity, so it will vary to minus infinity to n. So I am correcting one. So that's why the limit will vary from k is equals to minus 2 to minus infinity to 4. So now we have to just multiply and add. So the addition will give you value of 10. So the output will be, the value of y4 will be 10. Now this is the final question. Here we have two sequence x1n and x2n have the same energy. Suppose x1n is given by alpha 0.5 raised to the power n un, where alpha is a positive real number and un is the unit step sequence. Assume x2 n given by under root of 1.5 for n is equals to 0, 1 and 0 otherwise, the value of alpha, and it came in GATE 2015. So first we will calculate the energy of our x1, because it says that the energy of both of this signal is equal, so it has same energy. So first find the energy. So energy expression is basically from our basic definition as n is equals to minus infinity to infinity mod of x1 n whole square. So it will be equal to summation n is equals to 0 to infinity alpha square 0.25 raised to the power n. That will be equal to alpha square from 1 minus 0.25. This is from the property of summation of an infinite GP. So the property says that if we have a GP in which the values are, suppose 1 plus r square, and we are summing it to some value which is tending to infinity, as we have seen that it is varying from n is equals to 0 to infinite, then the summation will be equal to 1 by 1 minus r. So here r is your 0.25, and similarly we are getting alpha square by 1 minus 0.25. Similarly, the energy of x2 n will be equal to summation n is equals to minus infinity to infinity x2 n whole square. That will be equal to 1.5, because it's a square, plus 1.5, because we have only n is equals to 0 and 1. So for n equal to 0 it will be 1.5, and for n equal to 1 it is again 1.5, and for all other value it will be 0. So it will be equal to 3. So now as it is said that energy of x1 and energy of x2 are same, so we will equate it as alpha square 1 minus 0.25 is equals to 3, and this implies your alpha as 1.5. So this is your answer. So we can write the value of alpha as 1.5.